For this section, we're going to be looking at physical applications. So in particular, we're going to be looking at work and force. So first, if we take a look at what we mean by force, okay, we're looking at force and pressure, okay? So force and pressure, okay, they go together, right? And the pressure changes with the depth, all right? So it's important to know that we're going to be looking at the integral, right, of your depth, okay? So in other words, we're looking at the change in y. So that means we're kind of looking at what's happening vertically, right? So the vertical depth, because that's when you think about, for instance, the force in a wall of a dam, okay? So think about that force, right, that's applying there. So we're thinking about the vertical distance there, the vertical depth. So we're going to be integrating in terms of the vertical distance, all right? So when we want to find the force of something, then we're going to see if we can identify what we mean by this rho notation. That just means your density. All right, then this G notation, that's going to be represented by gravity. And then again, your depth, okay, that's going to be kind of the same thing as saying your distance. And then your length, that could also sometimes be referred to as the width. All right, since we're kind of thinking about looking vertically at something, and so sometimes the changes of your volume could change horizontally rather. So we're going to be maybe thinking about that as your width, okay, as opposed to the length. Now, when we look at the work, okay, again, we're going to be looking at that in terms of the change in y. And so you can see here, there's several different ways in which we can kind of show the relationship between work and force, all right? But the main thing we really want to focus on is how will we actually find how much work is required to, say, pump out water from a tank, right? Well, again, we still have these key things that we're going to look at. We have the density, we have the gravity. Now we're going to look at the distance in this case, all right? So remember over here we said the depth, well, that's going to be similar to having our density, and usually we like to denote that as a function, dy. And then we'll multiply that by this a. This is the same as saying your area function. So a of y, and again, it's in terms of y, okay? And so we're going to use this formula here when it comes to finding how much work is required to do something, okay? And so we can remember some of these nice numbers in which we have for the acceleration. We know that's the same as 9.8 meters per second squared. Okay, that's due to gravity. And then our density, in this case, if we look at the density of water, then we're going to have this nice notation rho, and that's just 1,000 kilometers per cubic meters. So let's take a look at this first example. It says we have a spring on a horizontal surface. It can be stretched and then held 0.2 meters from its equilibrium position, okay? And then it can be done with a force of 18 Newton. Okay, so let's think about what we want to do. So first it says, well, how much work is done in stretching this spring 4.5 meters from its equilibrium position? All right, so when we think of the equilibrium position, just kind of think about its starting point. All right, well, before we can figure out how much work it's going to take, we need to make note of something, okay? So we're going to make a note of a law that's referred to as Hooke's law. Okay, this is going to give us some information about force. Okay, so we're going to end up needing to find a force function, and we're going to just set this equal to k times x. Okay, well, let's see what exactly does this mean. Well, the x, that's going to denote your displacement. Okay, so you can think of your displacement or your distance, right, in which you are pulling or stretching something, okay? And then your K, well, since we're talking about the spring, that's just going to represent the spring stiffness, okay? So that means how much there do we have, okay? So that represents the spring stiffness, okay? All right, so since we're trying to find how much work needs to be done, then that means we need to know something about the force function because the work is just the same as finding the integral of the force, okay? So that means we first need to find our force function. All right, well, we are given the information of how much force that it takes. So it's going to be 18 newtons. So we know our force is 18. And then we have our stiffness. And then we have how much, right, our displacement that we are stretching it. Okay, so that's going to be our x. All right, so now if we wanted to find what the stiffness is, then we will want to solve for k, and we get k to be 90, okay? So now that simply means that our force function can just simply be rewritten as 90x, all right? Well, now that we have that, then that means we can go ahead and find our integral, okay? So let's see how to set it up. So how much are we stretching it? Okay, so we are stretching it at a distance of 4.5 meters, okay? And we're doing that from its equilibrium position, right? So again, we said that's your starting point, okay? So if you think about your starting position, right, your starting point, well, we started at 0 meters, right? And then we went up to 4.5 meters, okay? And then again, we said our force function was 90x. So now we just simply want to find the integral of 90x. Okay, so you would do what you would normally do in terms of finding the integral and evaluating. And when you do so, then you get 911.25. Okay, and so since we're talking about how much work, then the units there will be joules. So that would be how much work is required in stretching that spring 4.5 meters. Okay, all right, well, what if we wanted to know how much work is done if we are now compressing the spring at 3.5? Okay, so the key word here is compressing. So we're going to see, well, what exactly does that mean? Okay, well, how much work? We know again, that's just the integral of our force function. Okay, from our starting point, we can say from A to B. Okay, well, we already know our force function from before, that's 90x. So now we just have to figure out, well, what should we put on the bounds, okay? Well, again, our equilibrium position, okay, we know that means that's our starting point. So we are still starting at 0, but now we are compressing, right, at 3.5. That means we're kind of like pushing it together, okay? So now let's kind of thinking of that going in the negative direction. So our upper bound is going to be negative 3.5, okay? So there you go. That's how you would set up the integral. And now we would just integrate it and then evaluating it at the bounds, okay? And when we do that, we end up getting 551.25, and then again, those units are joules since we are talking about how much work.